Okay, so I'm very excited to introduce my next speaker, uh, Danai Koutra. She actually is a Maurice Wilm Assistant Professor in Computer Science Engineering at the University of Michigan, where she leads the Graph Exploration and Mining at Scale lab. Her research focuses on practical and scalable methods for large-scale real network and has applications on various domains, including neuroscience, organizational analytics, and social sciences. And her research interests including large-scale graph mining, analytics of multi-source network data, graph summarization, similarity and matching, and anomaly detection. She has won several awards like CKDD Rising Star Award, a Facebook and the Google Faculty Award, and also a prestige NSF Career Award, and also Amazon Research Faculty Award and Precision Health Investigator Award, and ARO Young Investigator Award, and Adobe Data Science Research Faculty Award, and many. Okay, and actually she has published broadly in top leading computer science conferences and have 8 award-winning papers. Her work has been covered by the popular press, including MIT Technology Review, and she is actually a program director of SIAG on data mining and analytics, and associate editor for ACM TKDD, a tutorial for KDD 19, and demo chair for CICAM 19. Yes, so she has very impressive achievement. So now the floor is yours. Let's
All
get
right.
started.
Thank you. Thank you for the kind introduction. Let me share my screen. All right. You're able to see, right? All right.
Yes, yes.
Great. Thanks again for the introduction, and thank you for inviting me. So there are a few updates. I'm currently an associate professor at the University of Michigan, and I'm also an associate director for the Michigan Institute for Data Science here. And with my students and postdocs, we focus on principled and scalable graph mining and learning methods. Now, during 2022, I'm actually on sabbatical at Amazon as an Amazon scholar, and I'm working on graph mining and learning for improving the search experience there. That said, the work that I'll be presenting today is based on work that I did with my students and collaborators from CMU, Aachen University, Adobe, and Google on graph learning beyond homophily. And I'll explain everything in a little bit. So, throughout the talk, I'll be talking about the task of node classification, which aims to predict the classes of the nodes in the graph given a small subset of labels. This task is important. It has many different applications in cybersecurity and recommender systems, where we want to infer the interest of the users based on their interactions with each other and preferences that they have explicitly or implicitly stated. And in industry, there are several companies that are actually using node classification in graphs in their production systems. Other applications include fraud detection, some type of classification over financial networks, let's say to identify trustworthy versus risky users. And there are other applications in different domains like computer vision, bioinformatics, and more. Now, a little bit more formally, the task of semi-supervised node classification is the following. We are given a graph with an adjacency matrix. Right, we have the connections between the nodes and also a node feature matrix. And we also assume that we have a few labeled nodes. In this small example on the bottom right, I'm using red and blue for the two node classes. Imagine this is a citation network, and the two classes correspond to AI papers and programming languages papers. And the goal is to find the class label of all the remaining nodes, everything that is shown here in gray. Now, there are a lot of different solutions to this for this problem, right? From traditional graph mining and machine learning, including iterative methods, probabilistic graphical models, graph-based regularization, and more. But more recently, graph neural networks have increasingly become popular for this task because of the way that they can leverage both the graph structure and the node feature information in end-to-end training. And they have achieved state-of-the-art performance in several benchmarks. So a lot of different models have been proposed. There's no way I can cover everything here. But this direction was popularized by the GCN model by Kiff and Welling. And I want to briefly describe this model because I'll be referring back to it within the context of our work. So a GCN usually uses multiple layers, and here I'm showing you the formulation for two convolutional layers. In each layer, GCN first propagates information over the graph and aggregates the representations from the previous layer within the neighborhood of each node. The propagation you can see here with the yellow arrows. And the aggregation in the simple formulation of GCN is basically a weighted average of the neighbor embeddings or representations. Now, after these representations are aggregated, they're being transformed by this learnable W matrix, shown here in green. And then some nonlinear activation function is applied to obtain the new representation for the next layer. Right? More generally, there are two key components: propagation and aggregation, and the nonlinear transformation. And most GNN models differ in how they do the message passing and the aggregation. Right? So since GCN, there have been a lot of different formulations that were proposed, right, using different aggregators, aggregating beyond the one-hop neighborhood, using sampling or some type of counting for speeding up computation, skip connections for increasing the representation power of graph neural networks, and so on. However, until quite recently, most of the work was focusing on graphs with strong homophily, where the linked nodes are similar in terms of classes and labels and features. So in a little bit more detail, what is homophily? In homophilous networks are those where most linked nodes are similar. You can think of this as birds of a feather flock together. And if you think about it, a lot of networks have this property. Like social networks, people tend to connect to others with similar political beliefs. Or in citation networks, usually papers cite other papers within the same research area. However, there are also a lot of cases of networks that exhibit heterophily. That's the opposite of homophily, right, where most linked nodes are different in terms of their features and class labels. Again, you can think of this as opposites attract. This is the case in protein structures, right? Proteins with respect to different amino acid types connect to each other. In e-commerce networks, it's known that fraudsters are more likely to connect to other accomplices rather than fraudsters. And if you think about knowledge graphs, where we want to do classification in terms of object types, node types, or entity types, there are often a lot of the connections, a lot of the edges, right, connect entities of different types. So there is, to some extent, heterophily. So again, until recently, this setting of heterophily was largely overlooked. So how do we measure homophily in a network? There are a lot of different ways we can do that, but in most of the talk, I will be referring to the edge homophily ratio, which is defined as the fraction of intra-class edges in the graph. So how many edges connect nodes in the same classes over the total number of edges in the graph. So this measure spans from 0 to 1. And 0 means pure heterophily, right? No nodes in the same class connect to each other. In extreme cases, a bipartite graph that would have this pure heterophily. And Pure homophily maps to 1. Most graphs are somewhere in between, right? Now, if we look at how different GNN models perform under homophily and heterophily, we see that under homophily, they perform pretty much as expected. This is a grayed out region in this plot, where you can see some models like GCN, GAT with attention networks, GCN Chebyshev, which uses Chebyshev polynomials, graph stage, and mix hop, right, compared to MLP, which is a graph agnostic approach, multi-layer perceptron. Right, so all these models work pretty well under homophily. They improve over the graph agnostic approach. However, if we look at cases with heterophily, and here I'm showing you one example with a pretty strong heterophily, 0.1, we see that MLP, this orange bar, performs significantly better than the GNN variants, which means that in this setting, the graph adjacency information seems to be misleading and causes models to fail. Again, this is not the case in every network with heterophily, but this is something that we observed in several cases. Now, I want to intuitively explain why this may be happening, and then later in the talk, I'll give you some ways to improve learning over these scenarios. So here, going back to the GCN formulation that I showed you before, and I want to show you what happens under homophily. Right, under homophily, we'll have something like this, where all the nodes connected to node 1 have similar class or the same class, right? This burnt orange labels. And remember that the aggregator in this case is essentially a weighted average. So this works pretty well. It actually denoises the neighborhood, right, and helps the model generalize generalize to the settings where, yes, nothing is perfect. Not all the labels are of the same class. However, in the case of heterophily, things are different, right? Where the central node is connected to other nodes that belong mostly to other classes. And in this case, the weighted average actually makes the representations indistinguishable, which leads to performance degradation for different GNN models. Now, I want to point out that, again, this is not always the case, and there are some works in the literature, especially more recently, that are looking into cases where GNNs can handle such settings under very specific conditions. But that said, heterophily remains a more challenging setting than homophily. So with my students, we looked into limitations of GNNs when learning over heterophilous graphs, and we identified some key design choices that can boost learning. Also, some of these designs came out of work that tried to jointly analyze heterophily and oversmoothing, two major problems that lead to performance degradation for GNNs. Beyond designs, we also propose some new GNN architectures that incorporate ideas from traditional message passing algorithms and combine it with end-to-end learning within GNNs in order to improve performance. So let me walk you through some designs that we found to be useful. The first and most important design is separating the ego and neighbor embeddings. So again, here you can see a little graph, and what the GCN would do, it would aggregate all these yellow nodes, the representations of all the yellow nodes. And what we're seeing is that actually separating the ego representation from the aggregated representations in the neighborhood can help. And this is because by definition, in heterophilous graphs, neighbors may have different features and classes. So by having two separate channels for the ego embedding and the representations of the neighbors, we essentially allow the model to learn different transformation functions for those and perform better. In terms of the combined function that you can see here, one very simple choice that does not blur the representations is concatenation. The second design has to do with going to a higher order neighborhood. So instead of just combining the representations of the one-hop neighbors with the representation of the ego with the ego node, we add a higher order neighborhood as well, highlighted here in purple. And the reason why this works is that in expectation, higher order neighborhoods may be homophily dominant. So by expanding to higher order neighborhoods, essentially we recreate a setting that GNN models perform pretty well. Homophily is more dominant there, so we can expect better performance. And the third design has to do with not only layer, but combining the previous representations as well. So this is also known as skip connection or jumping knowledge networks. There was an ICML paper that introduced this. And the reason why this works is that collecting information from a spectral perspective, it is known that the GCN style layers act as low-pass filters, but under heterophily, there's more information at higher than lower frequencies. So by concatenating these different representations, we're actually maintaining more of the information, the higher frequencies, and that leads to better performance. So as an overview, I've talked about three designs. The first one models the ego and neighbor representations distinctly. The second one models the representations of neighbors at different distances distinctly. And the last one uses representations at different layers. Now, these were not new designs even at the time when we did this work, but we focused on how these designs can help under heterophily, both theoretically and empirically. And we combined all of these designs into a model that we call H2GCN. And in this table, you can see that some methods like GraphSage or MixHop use a subset of those designs as well. So a few results on synthetic benchmarks first. Here we control the homophily in the graph. So we go from 0 to 1, strong heterophily to strong homophily. And the features in these graphs come from Cora or an open graph benchmark dataset in Amazon Graph.
Danai, we cannot see your slides at the moment. Do you think you can reshare it?
Oh, let me see. Yes, sorry. I don't know why this happened. Can you see now? Okay. All right.
Yes.
Yeah. Perfect. So just again, I'm not sure where you stopped seeing my slides, but here you can see the test accuracy for graphs where we vary the homophily from 0 to 1. That's the x-axis. And then the two plots correspond to graphs that have different features sampled from Cora on the left or products on the right, NodeGB benchmark. And what we see is that the model that we have that incorporates the three designs has the best trend overall and outperforms models, especially under heterophily, and does not trade off performance much in the case of stronger homophily. And this is something that we also see on real benchmarks. So you can see a bunch of different data sets ordered from strong heterophily to strong homophily. And below that, you can also see different stats, like how many classes we have in these data sets and nodes and edges. Now, you can focus on the last column that has the average rank of the models across all these data sets. And what we can see at a high level is that the variants that incorporate the designs have consistently strong performance throughout the full spectrum from low to high homophily. And also other models like GraphSage or GCN Chebby that have some of these designs also perform better than models that do not incorporate any of them. Now, another thing that I want to mention briefly is that in a more recent work with my student Zhong Zhu and others in the group, we found that a subset of those designs, especially the separation of ego embedding and neighbor embeddings and the skip connections, can also boost robustness to adversarial attacks in networks. And this is happening because those two designs allow better access to information that remains unperturbed when we have structural attacks, right? We have access to the features of a node and also access to representations from layers that don't have too many propagations. Another thing that explains this observation is that most structural attacks are heterophilous. So they either add links between nodes of different classes or remove links that connect nodes within the same class. I'm not going to go into more details for this, but if you're interested, I have the pointer to the work at the bottom. What about other designs that are useful? So with my student Yujun Yan, who will soon be faculty at Dartmouth, we looked at analyzing two key problems in GNNs from a unified perspective and came up with designs that can help address both problems. So the two problems are heterophily that I've been discussing so far, and oversmoothing. So oversmoothing is this problem where a GNN performance does not improve as the number of layers increases. And these two problems have been studied a lot independently. But more recently, there have been some works that see empirically that some methods that tackle heterophily do well in oversmoothing and vice versa, but without further explanation. So in this work, we looked into analyzing both problems together, right? And at a high level, they both lead to performance degradation due to indistinguishable node representations. So the key idea behind our theoretical analysis was to track how the node representations move over different layers. Like, do nodes move towards the representations of nodes in different classes or the same class? And try to explain what we observe in terms of performance. So at a very high level, what we found is that for heterophilous graphs, the representations of most nodes tend to move towards the representations of nodes in different classes, even from the first layer. While for homophilous networks, the representations move away from the representations of nodes in other classes at shallow layers, which is what we want. This leads to smaller misclassification rate or better performance. But as we go to deeper layers, the representations tend to become more indistinguishable. So again, there are a lot of theoretical details that I'm skipping here, but what I want to highlight is that we profiled nodes based on two properties here. Their local homophily, that is how homophilous is a one-hop neighborhood of a node, and the degree of a node relative to the degree of its neighbors. And what we found is that the interplay of these two properties that you can see also here it gives rise to three cases of node behaviors, two of which lead to higher misclassification rate or performance degradation. And these are case 1 and case 2. So based on these, we identified two more designs that can help, and those are one, degree correction, because actually one thing that we observed is that not only heterophilous nodes are problematic, but also highly homophilous nodes that have low degree. So what degree correction tries to do is it tries to upscale the relative degree of nodes that fall into this class, and it improves their classification performance. And the other design that is helpful is signed messages. So instead of allowing only positive messages to be exchanged between neighbors, right, basically the representations, we allow negative messages as well. And the intuition behind this is that we want neighbors that belong to different classes to send negated messages. So let me show you some results here. So this table is very similar to the one that I showed you before. It has the same data sets, but now we've added here some methods that can tackle just heterophily. Those are highlighted in yellow. Methods that tackle oversmoothing are highlighted in blue, and then orange color is used for those that are tackling both at once. And what we observe is that the model that we introduced that incorporates those two designs, the degree correction and signed messages, performs consistently well throughout the spectrum. Right, you can see the average rank is 1.78 compared to other methods. And not only that, but it's also very robust to oversmoothing. So you can see here for just two data sets, and we have more results in the paper, you can see for two data sets that as we increase the number of layers from 2 to 64, the performance increases, or at least it doesn't decrease significantly. Now, I talked so far about 5 different designs. Before I conclude the talk, I want to just mention that there are also different approaches to handle heterophily. And one of them is to design models, new GNN architectures that explicitly handle this case. And this is what we did in a IIII paper led by my student Zhang Zhu and with collaborators at Adobe. So in this work, we try to leverage a notion from a traditional message passing algorithm called belief propagation. And that notion is the compatibility matrix. The compatibility matrix essentially says what is the probability that nodes that belong to the same class or different classes are connected to each other. So in the case of heterophily, the off-diagonal elements are bigger. It means that nodes that belong to different classes are connected. So in this work, we, instead of doing the propagation and aggregation like in the original GCN formulation, we do compatibility-guided propagation, and we learn this compatibility matrix by leveraging the end-to-end training that GNNs offer. Again, you can see more details about this in the paper since I don't have time to go through that. So to conclude, we focused on some limitations of GNNs in heterophilous settings, and we saw that leveraging distinct representations at different levels can help, not only with performance, but also with robustness, especially to adversarial attacks. I also briefly mentioned the work that we have that that analyzes heterophily and oversmoothing jointly, and gives rise to some additional designs that can boost performance, and mentioned more a way to generate to develop an architecture that combines traditional methods from graph mining with GNNs and end-to-end training. There are a lot of future directions to be explored. One thing that I hinted during my talk is that heterophily is not always a challenge. So gaining a deeper understanding about when it poses challenges and when we need to leverage specific designs or architectures is important. And we have a blog post where we visited heterophily within GNNs. There are other things that can be or deserve to be explored, like the interplay between heterophily and notions like robustness, fairness, explainability. And there is also a very big need for larger and more diverse data sets with heterophily. I didn't highlight that much when I was showing results, but if you go back to those tables with the real data sets, you'll see that most data sets with heterophily are quite small, and their structure is quite unique compared to the power law degree distribution-based graphs, like social networks or citation networks. So these are the papers that I refer to throughout this talk, and there's also a lot more relevant papers from others, not within my group, that tackles different aspects of GNNs and heterophily. And with that, I'd like to thank you, and I'm happy to take questions if we have time.
Yeah, thank you, Danai, for your great talk. We have two questions from the audience. The first actually talk about the heterophilia related to oversmoothing issue, but you mentioned a little bit in your slides already, right? And
Yes.
the second question is concentration of ego and neighbors increase the number of dimensions. Does this become a problem? I'm not sure. Is this a, yeah, can you talk a little bit?
Yes. Yeah, you are right. We are learning bigger representations there. So it does impact uh, the computational speed as well, right? You need more memory, more time to generate those. Um, it's and the question I think is, what is the application, and do you need better performance, or is speed the main consideration there? So I think that can help with deciding. Another thing that one can do is reduce the representation, the embedding length, right, of um, uh, the embedding dimension, right, so that the total representation, the final representation that is being learned, is acceptable and within the runtime limitations that may exist.
Thank you very much. Thank you.
Thank
Bye.
you for inviting me.
Bye.